Hello everyone, today we're going to talk about PBL Level 1 Physics project. A couple of years ago, one of my students was asking me, "Sir, how do we measure the thickness of a hair?" And I didn't really think about how you measure the thickness of a hair because it's in biology stuff. I'm a physicist. And I actually made some research about it, and I've seen that you are using microscope to measure that. And it's very simple. You just put that in the microscope and you just look at it and then you just measure the thickness of it. And first, that was very simple for me. Second, that was a biology thing. And as a physicist, I don't like to talk about biology to my student because my students know that I don't really like biology. So I thought about there should be a way to measure the thickness of a hair by using physics. And I made some more research about it, and I found that Thomas Young, who is a British scientist, actually found a method to measure the thickness of a hair. But of course, he didn't mean to measure the thickness of a hair. Thomas Young actually figured that light is acting like a wave and a particle at the same time. And with this diffraction phenomenon, he was able to prove that light has a wave property. So, and with this phenomenon, with this diffraction method, we are able to measure the thickness of a hair. And I was so excited that I'm going to be able to explain that to my student by using diffraction phenomenon. What we're going to need for this experiment, we're going to need a laser, and that's a red laser. And you have to be careful with the laser because once you plug that in, you're going to have a really strong light beam that is coming out, so you should never look at the beam directly. So you should be very, very careful with that. And we're going to need a single slit or double slit, and that's from Pasco, and that's a multiple slit set, and then you have a bunch of slits, and that has 4 different types of double slits, and you can use any of them depending on which one, how you want to do your experiment. A holder to be able to hold this single slit or double slits or your slits, whatever you're going to use. A screen to be able to measure your distances. And you're going to need an optic bench that is going to hold all of your materials. Finally, you're going to need a ruler to measure around like 10 centimeters. First, we're going to mount our laser to an optic beam. So first, you mount one side and then just push from the top. Next, our accessory holder, doing the same thing. Next, we're going to place our slit to the holder, and you just mount it, push it a little bit, and you can turn this around the mount, and you can also turn this to be able to adjust which slit you want to use. And we place our screen to the other ends, and by the same method, just push it in. To be able to power the laser, you need to plug in and make sure that it's off when you plug it in, and you're going to turn it on once you are ready. And there's a horizontal adjustment. You can move it on the x-axis, your laser, and your vertical adjustment. By turning this, you're going to adjust your laser up and down. Next, we make sure that our laser is passing through our slit, and now you can see the red light over here, and it's passing through the slit. And over here we have A and D, 2 labels, and here you can see their description. A is the width of the slit, and D is the separation in between 2 slits. And now we're ready to do our experiment. How are we going to do our experiment? Basically, we're going to use Young's double slit experiment and diffraction equation. Over here, we're going to have X, D, lambda, and L. And I'm going to show them in the experiment setup in a minute. But X is going to be the distance in between 2 bright bands. So in double slit experiment, basically, when light passes through a slit, it diffracts. It's going to have bright bands and dark bands. And this X is going to be the distance in between 2 adjacent bright bands. Next one is D, and we already talked about that. On the slit, that is the distance in between 2 slits. That's important. That D is the distance in between 2 slits. It's not the width of the slit. And lambda is going to be the wavelength of our light, which in this case our red laser. And L is going to be the distance from the slit to the screen. And how are we going to use this equation? So basically we need to isolate our lambda over here to be able to find the wavelength of our light. And in this case it's going to be x over L times d. And d is a constant value and where you can look at it from the slit. And we're going to have x over L. So once we get the ratio of x to L, then we're going to be able to find the lambda. How are we going to do this? L is the distance from the slit to the screen, and x is basically the distance in between two adjacent bright lights. So we can change the distance, which is L, and we can measure x. So if we draw L to x graph, and if we get the slope of that and multiply that slope with the d, then we can find our lambda. So we're going to have the table of L to x, and since we can change the L, we're going to measure the distance from screen to the little slit, and we're going to start with 0.5 meters, which is 50 centimeters, and then we're going to increase that distance by 10 centimeters, and we're going to have 6 different data. And then we're going to find our x values for each length, and then we're going to have our graph. Measurements are very important, so we are going to put our screen to 0 centimeters, and we make sure that the edge is cutting the 0 centimeters. Next, we're going to place our slit and make sure that slit itself is going to be 50 centimeters from the screen. So that should go to 50. Don't get confused with the markers. Holder's mark, which is at 52. So there's a 2 centimeters difference in between the slit and the mark. So make sure that you are placing the slit at 50 centimeters, not the mark. Next, we are going to measure our x. We place our screen at 0 centimeters, and we place our laser, the slit at 50 centimeters, and that's our L. And now we are going to measure the x. X is from basically from the center bright line to the next one. So we need to measure that distance, and you better mark those 2 points, and then you can measure those 2 marks with a ruler. Or if you want to make a better, more accurate calculation, you better place 1 mark at one of them and then count 1, 2, 3, 4, 5, 6. So basically this is the distance of 6 bright lines. So if you measure that distance and divide it by 6, then you're going to find your x, but that's going to be more accurate data. All right, now we're going to put our data to our table. And for 0.5 meters, I measured 0.7 centimeters divided by 5. And for this, 0.8 centimeters divided by 5. For that, 0.9. And that's going to increase by 0.1 for each. My data was pretty accurate. And that is 1 centimeters divided by 5. 1.1 centimeter divided by 5. And that's 1.2 centimeters divided by 5. And that is 1.3 centimeters divided by 5. And over here, you have to make sure that you are using the correct units, because these are all measured in meters, but this is 0.7 centimeters, and we measured 5 bright points, distance in between 5 bright points, and then we divide them all by 5. Make sure that you are using the correct units and you are dividing it by the correct number. And now we're going to draw our graph. On the x-axis, we're going to have our L, which is the length, and that's in meters. And we have all of the data, and we start from 0.5 meters, which is 50 centimeters. And on the y-axis, we're going to have our x, and that's in meters again. but our data is going to be in millimeters, so I didn't want to put 0.000. So I multiply all of the x's by 10 to the power negative 3. And now we're going to place our numbers. And I have 1.4. That's 1.5. That is 2. That's 2.5. And that's 2.9. Each is going to increase by 0.1. And now we're going to put our points. Our first point is 1.4 and 0.5, which is that point. And next point is 1.6 and 0.6. And now we place all of our points. Now we're going to draw the best fit line. And for this is going to be a straight line. And since this is a pretty accurate data, we just need to find the slope of that. And over here, you just pick 2 points from the axis. And this is my second point. And my delta x is 0.6 times 10 to the negative 3. And my delta y is 0.3 meters, and that's also in meters. And our slope is basically rise over run, so 0.6 times 10 to the negative 3 divided by 0.3. All right, in the final stage, we're going to multiply our d with 1 over slope. And our slope is over here. And once you calculate the slope, it's 0.5 times 10 to the negative 2. And if you multiply it with our d, at the end, we are finding our lambda as 650 nanometers. And which is pretty accurate because the actual wavelength of the red light is 651. And that's pretty accurate. So how do we measure the thickness of a hair? So what you do is, you're going to bring the hair in front of the laser and then make sure that laser is passing through the hair. And in this case, your hair is going to act like a double slit. So on the screen, you're going to see bright and dark bands. And by using the same equation and the same method, instead of finding the lambda, you can find the thickness of your hair. Now once we place the hair in front of the laser, you can see that it's acting like a double slit because you're having brightness and darknesses. And the distance in between bright and dark points, that's your x. And your thickness in this case is going to be your d. So you're going to solve the same equation for d. All right, what else we can do with the diffraction phenomena? We just measure the thickness of a hair. I don't think so, because that's very important phenomenon in physics, because that's explaining wave behavior of light. So scientists are using this diffraction principle to measure the focus of a camera and telescopes. So it's very important because once you change the distance in between the laser and the slit in the screen, they are changing the distance in between the bright and the dark points. So they are using this phenomena in telescopes, cameras, And in CDs, there are tiny diffractions, tiny slits basically on the CD, and that's how you read the data. So we are using this diffraction basically every day in our lives, but we just don't know what we are doing. So basically that's diffraction principle, and that's what we explained today. Thank you for watching.